The topic for this series is going to be EOS models and how they're made. First, we're going to be defining what we mean by an ideal gas. Then we're going to be looking at some of the main variables. We'll then take those variables from a microscopic to a macroscopic scale. In the end, we'll take a sneak peek of what's coming in the next week. Let's get started by taking a look at the assumptions of an ideal gas. We have a container with a bunch of different particles. The first assumption we're going to make is that all the particles are spherical, and they have to be sufficiently small. We'll then give them some random velocity in a random direction. Repeating this again, we can now simulate how these particles are going to interact, assuming that they're not going to interact with each other because they're sufficiently small and there's no interactive force, and the collisions with the wall are perfectly elastic. The question we want to ask ourselves now is, what happens when we change some of the initial parameters? The first thing we want to take a look at is, what changes when we change the initial velocity? Here we have three systems, one with half the speed, one with the initial speed, and one with twice the speed. Let's take a look at how many collisions happen in each of these cases. From the collision count, we can see that a doubling in speed approximately doubles the number of collisions. Now let's see what happens when we change the number of particles. Once again, we have three systems, one with 5, 10, and 20 particles. Let's see how it changes the number of collisions. Not surprisingly, we see that the more particles, the more collisions there are with the wall. Finally, we want to see what happens when we change the size of the container. Now we have three separate containers, one more narrow and one a bit wider, and we'll see how many collisions there are now for each of these cases. What we see is that a smaller container leads to more collisions, while in the larger container, the particles have to travel further to hit a wall, leading to less collisions. Trying to link these microscopic variables to something more macroscopic, we see that the collisions enact a force on the container, which is equivalent to pressure. The surface area of the container is going to be equivalent to the volume. And then we have the velocity, and this is going to be related to the temperature of the system. Finally, the number of particles is going to be equivalent to the number of moles. In fact, this is what a mole is. To summarize, when the number of collisions goes up, the pressure goes up. And when the surface area of the container goes up, the pressure goes down. When we increase the velocity, the temperature is going to be increasing. And as we saw, the number of collisions and therefore the pressure is also going to increase. When we increase the number of particles, the number of collisions went up and therefore the pressure also goes up. These sets of relationship combine to develop what we know as the ideal gas law, which can be written like this. In the next video, we're going to take a look at what happens when we don't have all the assumptions of the ideal gas law, meaning that we add a little bit of attractive and repulsive forces between the particles. Thank you for watching, and I'll see you in the next video.